Hello and welcome to this video on polynomial modeling. So in this example, we're going to be using a polynomial expression and equation to represent a situation in the real world. That is what modeling is, and it's an application of math towards the real world in general. So in this particular situation, we have a company who is manufacturing open-top rectangular boxes, the type of which you might see if you were working in an office or if you were moving and you wanted to store papers, files of importance. Those are the type of boxes that we're talking about here. So they have a 30 centimeter by 16 centimeter sheet of material, and that might be cardboard, for instance, if you're making a normal box you might see or might buy at a kind of Office Depot sort of store. And so these bins are made by cutting out corners of the same size from each corner and then bending up the sides afterwards and then kind of taping, sealing the corners using some kind of method. You might staple it if it was cardboard. However they're going to put it together, that part isn't really as important. So our goal is, in general, to create a box that would be the largest possible. And we are starting out with the same size piece of material. And then we're going to see, well, what kind of dimensions are possible that might maximize the volume. And we'll see, well, can we think about what domain and ranges are possible? And we're going to do kind of create our equation by hand and then look to use Desmos and a graphing technology to figure out what the maximized volume might be. So for starters, let's kind of think about what is really going on here. So in this example, we have a 30 by 16 rectangle here. So when they kind of cut out each one of these four squares, they're going to fold along the dotted lines. So kind of these sides would kind of fold upwards, and then these two sides as well would kind of fold upwards. So you can see how, like, without the corners, you could kind of fold it into a box. So now, when we are kind of making this example at first, we want to think about a couple examples first before we start making an equation. So if I cut out corners, let's say that we'll make a table. So corner, size, and then we have volume. So let's say, for instance, to start with, we have a 1 centimeter corner size. So that means that in this picture, these corners are kind of 1 centimeter, 1 centimeter. So maybe we'll draw it a little bit bigger here. So if I have my kind of one piece here, so we know that this top part is 30 centimeters and this side is 16 centimeters as well. We are saying in this first example that our corners are 1 centimeter. So that means we kind of have a corner here and in all four of our corners, and these are the same size as each other. So this is 1 and that is 1 right there. And then we have 1 and 1, 1 and 1. Now the fold lines, these dotted lines, to make it into kind of a 3D box, would kind of be these dotted lines here. And so if we want to think about how we would create and figure out what the actual volume for this would be, well, if I take away 1 on each side, so these are both 1. So if I took 1 and 1 away from 30, well, that would give me 28. So my length would then be 28, my length. For my width, I have 16 on the right-hand side here, but I took away 1 and then 1 more down here. So that would be multiplying by 14. And now if I am folding up the sides, so if I'm folding along this dotted line right here, the side length, the depth or the height of this would be 1, because you kind of fold up the sides, and this part right here would be the height. So times 1 for our height. Now all we'd have to do would be to grab a calculator, and we are doing 28 times 4 times 1. 28 times 14 times 1 equals a volume of 392 centimeters cubed. Our cubic centimeters, that's a three-dimensional way of measuring units. So that is one example. We figured out that 1 centimeter corners are 300, give us a box that's 392 cubic centimeters of volume. So if I wanted to, say, double that corner size, and so we would have a 2 for our 2 centimeters. So that would basically be kind of, if you could draw in a picture for that, but I would basically be taking 2 away from each side of the 30. So my new length would be 30 minus this 2 twice. So now it'd be down to 26. And then I would take the new corner size of 2s, so it'd be like a 2 right here, 2 and 2 right there. So I'd be taking away 2 twice from 16. So 26 minus 2 equals 12. But now since my corners are 2 by 2, well, that means when I fold that side up, I'm going to be going all the way to 2 for my height. So that's some different numbers right there. So now if I check that volume out, so I would then have 26 times 12 times 2. And that equals 624 centimeters cubed. So if you think about how those might compare, if I do 624 divided by 2, well, that's 312. So I doubled the corner size, but I less than doubled my volume size. So we definitely don't have a linear relationship. So it could be quadratic or cubic or other polynomial that might be representing what is happening here, but we know it's not linear. If we double our x, our y's should kind of follow that pattern too, if it is in fact a linear pattern. And that is not what had happened here. So if we think about, we went up in volume to 624 cubic centimeters. And so if I wanted to keep going through this process, I could keep guessing and checking to see if I could get a bigger volume. For instance, if you did the same thing and you went all the way to, say, let's say 7 centimeters. So I would take away 7 twice from 30, which would bring me all the way down to 16. And I would take away 7 twice from 16. So that width would go all the way down to 2. And then my height would then be 7. So 16 times 2 times 7 would equal 224 centimeters cubed. That's even lower than what we started with 1 centimeter. So you can see that if we increase from 1 to 2, well, our volume almost doubles. But if we go all the way up to something like 7, well, now we're going down in volume because our box is kind of decreasing in size, even though it's much taller. So that was 224 cubic centimeters. So now our goal is, well, we don't want to keep guessing and checking because we could try any number of corner sizes and decimals and all these things that would lead us eventually to maybe the maximum volume that we could be looking for. But what we really want to do is have a systematic way of doing that. We were looking for a polynomial that would represent this situation. So we're going to be looking for an equation for volume. So we're looking for v of x, where x is the side length of a corner. And we're trying to figure out what v of x could equal in this kind of situation. So if we think about what happened, so if we look at first our height, well, we know volume is going to be length times width times height. So we got to have 3 parts at the very least. Well, we know our height, first of all, when our corner size was 1, our height ended up being 1. When it was 2, it ended up being 2. And when it was 7, it was 7. So our height is just going to be whatever our x corner size is going to be. So the hard part is getting length and width for this volume equation. Now we know the maximum our height and width can be are 30, and we also know that it's 16 right there. But obviously we can't go all the way to 30 and 16 because then the corner would be the whole box, which that's not what we want. So now how we figure that out for at least the length up here at the top, well, when it was 1, well, we took away 1 twice from 30. And then the same thing with 16. We took away 1 centimeter on each side from 16. So what that means we can do is that for my length, and we'll do the length in blue. So length is 30 minus 2 of our side corner lengths. So 2 of these lengths. So like this one and this one, we have 2 of them. Our width is going to be pretty similar because for our width, well, we take x away twice from our total width of 16 centimeters right there, 16 centimeters. So that is our width, 16 minus 2 of those corner lengths. And then finally, we already knew our x value. And so we have a volume equation right there. And you could leave this in our factored form or change that into standard form by multiplying everything out. So maybe we do some quick practice with that. So when we're multiplying parentheses, we have 30 times 16 that we would do first. Well, so that would give us 480. And then we do 30 times negative 2x is negative 60x. Negative 2x times 16 is negative 32x. And negative 2x times itself is 4x squared. And then all of that is being multiplied by another x value. So x times all of that would give us 480x minus 60x squared minus 32x squared plus 4x cubed. Now all that's left is put it in standard form. So reordering it and combining like terms, you would get 4x cubed minus 92x squared plus 480x. So now our last thing here before we go and try to maximize or find the highest point of this cubic trinomial will be to figure out what our domain and range might be. And more specifically, our domain. Because we know our range was going to start, well, it's got to be bigger than 0, but we're not sure where that maximum of our range would be. That's kind of the point of us doing this. So to figure out our domain, we have to look at our factored form. So we don't want x to be 0. If x is 0, then there's no corners at all, and we don't have a box. So x has got to be bigger than 0. But we also don't want our length or our width to end up being 0 either. So we need to make sure we're not doing 16 minus 2 times something that would get you the whole red part here to be 0. We also don't want to be subtracting more than 16 from 16. And then the same thing in blue. So basically what we need to write here is that we need our length, which is 30 minus 2x. We need that to be greater than 0. So if I add 2x to both sides, I would have 30 is greater than 2x, and divide by 2, I get 15 is greater than x. So that's basically saying, or x is less than 15. So we know that our x has to be, well, greater than 0 from what we already talked about. Also, it can't be bigger than 15. But if we look at our red one, so if we have 16 minus 2x for our width, so our width is 16 minus 2x. That has to be bigger than 0 as well. So if I do the same steps, add 2x to both sides, and then divide by 2, I get that x has to be actually less than 8, because we don't want our width or our length to end up being 0 or even negative. And a negative length doesn't really make a whole lot of sense at all. Now, so what that means is that since we know x has to be less than 8 and less than 15, we can just look at the x minus 8, x less than 8 part. So what we can say about our domain of x, which remember, x represents the side length of our corner cutouts, is that we can say that our x has to be somewhere in between 0 and 8. And that's the only part of the graph in our next part of the video that we're going to be looking at, and we want to be finding the maximum y value or for our volume somewhere in between 0 and 8 centimeters. And that's what we're going to be looking at next. Now that we have Desmos graphing pulled up, we can look at how we can maximize our volume polynomial equation to find the biggest possible volume of the box that we started with in this problem. Our work so far is on the left-hand side of our screen. We have our volume equation that we just created together. We remember that volume is length times width, and this should be a height right there. And we have our length, width, and height separate in each equation that we've already established so far. Now you'll notice that in Desmos you can kind of set up your equations. So you can use function notation here, and we already know the length, width, and height here, and I can kind of define those in the bottom 3 rows if I wanted. So I could kind of click on each of these and have each of those equations graphed, and we'll look at that once we have everything in place. So now that we obviously can't see much of our equation here, and we want to kind of make it a little bit bigger so we can see it using the domain we have set up. So to start with, we want to think about our domain. So if we look on domain, well, we know x is the side length of the corners. That was how we defined it. Our lowest x value we know was supposed to be 0, and our biggest x value was 8. We couldn't get any farther than 8. And we probably want to just go up by ones. So that's what the step means. We don't know exactly what our biggest y value is going to be. We do know it's going to start at 0. And we also tried 7, and that ended up being 224. We tried 2, that was 624. So maybe we go past 624 all the way to 700. And we can see, well, we can't quite see it all. So we maybe want to extend it another 50, maybe all the way up to the next round number, 800. And we don't want to go up by 200 each time. So we go up by 100, maybe let's go up by 50. And now we can see our full equation. You notice that these are the same. We can just get rid of this. And we're looking at our red equation, which this isn't the full cubic polynomial, but we're only now looking at the part of the domain that makes sense for our box problem that we've been working on during this video. Also, we forgot to label our y-axis as volume. Now you add that in. So with Desmos, if we click on the top of this, we can see that 3.333 gives us a maximum volume of 725.926 cubic centimeters. So if you were this company, what that tells us is that if they cut out corners that are about 3 1/3 centimeters on each side, that would maximize the volume of this shape of rectangular prism, I guess you could call it. And you can see that as you kind of go up in corner lengths, your values are climbing really quickly. But then as we saw with trying 7, as you go past this maximum, Well, now our volumes are starting to get lower and lower as you get closer to your biggest corner sizes. You can see 7 is all the way down here where my cursor is, 7 and 224. So if you wanted to figure out exactly what the length, width, and height are going to be, we could use these equations that we just established there. So if I made x equal to 3.33, let's just get rid of that. So 3.333, and then do the same thing times 3.333, and then x here, 3.333. Well, we can see that our length ended up being about 23 1/3 centimeters. Our width would be about 9 1/3 centimeters. And we have effectively maximized the volume of this rectangular box using a polynomial equation. And that concludes this modeling example. Thank you for watching.